Hello, in this video, I'm going to talk about how we convert this form of data centering into, which might not be super intuitive, into the centering formula where we actually use the centering matrix. So to define some things, mu of x, it's the terrible mu, represents the column-wise average of our matrix X. So to put that, in text, so we get the sum from I to n of X I transpose. So in this case, we're averaging over our features. So if we have D features, we're going to get the average of D1 values, the average of D2 values, etc. So like if X is equal to, so our big X we've always defined as X1 transpose, X2 transpose, dot, 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 where these are each samples. Another way we can write this is, well, if we have D features, this really becomes something like this, where we have X1, 1, which is the first feature of X, X1, 2, dot, 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 and then we have same for X2, X2, 1, X2, 2, dot, dot, dot. And we go for all n samples. So what mu x is doing is it's averaging along the columns. So with that in mind, I think the first step that we'd want to do is to create some sort of vectorized equation of this. So each component of big X is transposed. Well, we can actually rewrite this equation as 1 over n times this one vector times x. So this one vector transpose. And so really what this would look like is, well, we have 1 over n times 1, 1, dot, 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 1, where there's n ones, and then times our big X, which will look like this, x1, 1, x2, 2, dot, 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 x2, 1, oh, sorry, x2, 2, dot, 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 and this goes on. And so what doing the product of this vector in this matrix will actually output is a row vector where this first value will be, x11 plus x21 plus dot, dot, dot. And the second value, I do not create a lot of space for myself. This next value will be, x12 plus x22 plus dot, 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 and then so on and so forth. And then we multiply this by 1 over n. So basically my point is, well, mu of x is just actually equal to 1 over n times this one's vectors transpose times x. Okay, so with that in mind, well, mu of x is actually just a vector. So in order to subtract, so if we have this equation mu x, in order to make this, a little bit more realistic, we have to somehow copy this vector for the amount of rows that x has, right? Because this is d, d by 1. It's a row vector. So since it's a row vector, well, we can just copy it n times by multiplying it again by a ones vector, right? Because if you remember the outer product, we have a column vector times a row vector. Well, this just copies this row vector, n times. So actually what it'll look like is this. Okay, so with that in mind, this equation becomes 1 minus the ones vector times mu of x, right? And so if we substitute mu of x here, we get, here, let's create some order right here. So mu of x is right here. Right here. So we have, well, x, this is actually just equal to this times the ones vector, mu of x, right? And so if we substitute our value of mu of x in here, we get this is equal to x minus 1 over n 1 transpose x. And, this is a constant, so we can do some rearranging. 1 over n 1 times 1 transpose x. Okay. The next step we can do is we can just move this x out, and so this is equal to the 1, the identity minus, right, because x times the identity is just equal to x. So we can move that x out and replace it with the identity. 1 over n, 1 transpose x. Right? And what you'll notice is, well, this right here is just c. So we're done. So this is equal to c of x.